Hello and welcome to Equity Education, the chemistry version. And today we're going to be looking at acids, bases and the ionic product of water. Again, it's a pretty long video, so if you want to split it into two, might not be a bad suggestion, but we'll go ahead and get started. So can you open your booklet? And we'll start with some definitions. So the Bronsted-Lowry definition. So an acid, we can describe an acid as a H plus or a proton donor, and I'm sure that you've seen these definitions before. A base is a H plus or a proton acceptor, and we can define an alkali as a soluble base that releases hydroxide ions, which are OH minus in aqueous solutions. And we'll quickly just write some acids. So an example of an acid is HCl, hydrochloric acid, nitric acid. Base, sodium hydroxide, ammonia, and again we've written some bases here. These are also alkalis, sodium hydroxide and ammonia. These are our most common ones, yeah, for our bases and alkalis. Right, so we'll move on. Quick point. So deoxonium ion, you may see this word and wonder what it is, and what it actually is that technically the H plus of an acid has been simplified in the most common reactions you will see. Really, a H plus is the H3O plus slash oxonium ion. E.g., so when we have an acid dissolved in water, it actually reacts with water to produce H3O plus. And this is our oxonium ion, which is generally simplified to H plus. Just a quick point, if you see it in any textbooks or on any other videos and wonder what it is. Okay, right, so moving on. A couple of more definitions that you might see come up. So amphoteric, a molecule that can react with both an acid and a base. E.g., do a quick example, because you might not have seen this before, water. So as we just said, H2O plus H plus can react to form H3O plus our oxonium ion, or it can behave as a base by accepting a H plus in this reaction as well. So we can say that water is amphoteric because it can react as an acid or it can react as a base. Okay, moving on. So a strong acid, an acid that completely dissociates in aqueous solution, e.g. HCl. I'm just going to use AQ as water. We'll dissociate to produce H plus and Cl minus AQ. If it means that it completely dissociates, that if I started with 0.1 moles of HCl, must mean that my ratio is 1 to 1 to 1. I must have 0.1 mole here and 0.1 mole here. A weak acid, an acid that partially dissociates. in aqueous solutions. Our most common example is ethanoic acid, which is a carboxylic acid. To produce this, because I'm writing quickly, you may have noticed that I've made a pretty big error. This obviously should be a reversible reaction. And we also need to say that not many of the ethanoic acid molecules will actually dissociate to produce the ethanoate ion and the H+. So we can say that the equilibrium lies far to the left. And this will be important later on. Okay? So, strong base. A base that completely dissociates in aqueous solution, e.g. NaOH plus AQ, and it will form our hydroxide ions. And again, if we have 0.1 mole here, because it's completely dissociates, we must have 0.1 mole of each of these. And lastly, a weak base, so a base that partially dissociates. In aqueous solution, we'll use ammonia as the example. And because it partially dissociates, must mean that we have a reversible reaction. Okay, so I've gone through that very quickly, and that's probably because you know this stuff already. Okay, if you're unsure about any of this, then go to my introductory video on acids. Okay, so moving on to conjugate pairs. So conjugate pairs, conjugate acid-base pairs. So in acid-base reactions, there are conjugate pairs, and they're said to be acid-base conjugate pairs. E.g., let's do an example of this. So in this example, we will have ammonia plus H2O forms NH4 plus OH minus. And then we'll quickly go through this. So in the forward reaction, the water donates a H plus to the ammonia. So my water has donated a H plus to the ammonia, which has formed an ammonium ion. The water is therefore an acid, and the ammonia is the base, which makes sense. So I can label these as my base 1 and my acid 2. In the reverse of the reaction, the ammonium ion is the acid, as it can donate a H plus or a proton. The hydroxide ion is the base, as it can accept a H plus or a proton, which means then that I am going to have my acid 1 and my base 2. So the ammonium ion and the ammonia are considered a conjugate acid base pair. The ammonium ion is the acid and the ammonia is the base, and therefore I can label these two as a conjugate acid base pair. It's a lot of words, yeah, but it's pretty simple and pretty self-explanatory. So just to make sure you've got it, have a go at doing this. So label the other two species as conjugate acid-base pairs and explain why. Okay, so I'm sure you've managed to do this, especially if there's only 2 species left. So this would be our conjugate acid-base pair. And we can describe it as a conjugate acid-base pair because H2O is the acid as it donates AH plus, and the hydroxide is a base as it can accept AH plus. Okay, so pretty self-explanatory, pretty straightforward. So we'll move on. So acid and base reactions as ionic equations. Again, this is a bit of revision for probably most of you. So I'd just like you to have a go at completing them. So all acid and base reactions can be converted into an ionic equation. Complete the ionic equation for the reactions, and obviously complete the whole chemical equation as well. Remember to balance it, okay? And then we'll go through it quickly when you come back. Okay, I assume we found this quite straightforward. So I have my acid plus my alkali, so I'm going to make a salt plus water. So NaC plus H2O. Remember our definition. So a salt is when the H plus of an acid is replaced by a metal ion or an ammonium ion. Now I'll go through the first one properly to show you how to work out ionic equations, but after that we won't bother doing it so much. So we'll write the state symbols in here, AQ, AQ, AQ and L. Okay, so remember, when you're constructing ionic equations, you split all the ionic substances that are aqueous here. So we would have H plus Cl minus plus Na plus OH minus goes to Na plus Cl minus plus H2O, and we leave H2O as a molecule because it's a covalent compound. Now we need to remove the spectator ions, and to do that we look at the oxidation states of the ionic compounds, the ions, and see if they've changed. Well, my Cl minus hasn't, my Cl minus hasn't, my Na plus hasn't, my Na plus hasn't. Something has happened with these, H plus to OH minus, it's formed a molecule, so that must mean that my overall equation is H plus. So OH minus forms H2O. Simple, yeah? For this one, again, remember you need to be able to work out the formula of the salt. Calcium is in group 2, so it's plus 2. NO3 is minus 1, so I need 2 of these. So I'm going to form a salt plus water. I need to balance it. There must be 2 of these here, which also means I need 2 H2O here. And again, if you go through the ionic equation, we're going to have H plus OH minus forms H2O. So you'll see a pattern emerging that even though we have different acids and different bases, we're still forming the same chemical reaction. And lastly, H2SO4 plus LiOH. I'm going to form my salt again and water. Lithium is in group 1. SO4 has a charge of 2 minus, so I need 2 lithiums. Then need to balance it, so 2 LiOH and 2 H2O, which means that my ionic equation will again obviously be this. Again, a bit of revision, and now we're going to move on to stuff that you may not have seen before. Okay, so pH. So pH, what does it do? So pH measures the concentration of H plus in a solution, and you need to know an equation to work out pH. So pH is equal to minus log the concentration of H plus. There's quite a few of these formulas that you need to remember, okay, and this is one of them. So pH equals minus log to the concentration of H plus. So calculating the pH of strong acids. Now we know that strong acids fully dissociate to produce H plus ions and anions, and we've already seen this example. So HCl plus AQ will form H plus Cl minus. And if we say if there is 1 mole of HCl in 1 dm cubed of the solution, what will be the amount in moles of H plus ions and hence its concentration? Well, I know from that if I've got 1 mole here, I must have 1 mole here and 1 mole here, because it's a 1-to-1 ratio. If it's in a 1 dm cubed solution, I must have a concentration of, we'll actually use the formula, so concentration equals N over V, so 1 over 1 gives me a concentration of 1 mole dm minus 3. Makes sense so far, I guess. Now we can calculate the pH of the solution. So my formula is pH minus log of H plus, and in my values, minus log of 1, which gives me a value of 0. So 1 mole, concentration 1 mole dm minus of HCl will have a pH of 0. Okay, so I would like you to have a go at doing these 3 calculations and see what you notice about them. Okay, so I'm sure you are able to do these calculations. So pH equals minus log to the base of H plus. You may notice I keep writing this down, it's so I don't forget it, and you should be doing the same as well. So I can do minus log of 0.1 minus log of 0.2 and minus log 0.3, which I'm sure you've noticed equals 1, 2 and 3. So this tells me something. This tells me that log is a scale of numbers based on powers of 10. And we use the pH scale as it is easier to tell the acidity or alkalinity of a substance or a solution, rather than just looking at the H plus concentration. So with big numbers or with very small numbers with the H plus concentrations, it's hard to tell whether the solution is acidic or whether it's alkaline. Therefore, by converting it into pH, we have an easy reference point to be able to tell what the pH is. Okay, so moving on. Calculating the concentration H+ from a pH value. So if we know the pH value of the strong acid, we can calculate the concentration of the H+ by doing the reverse reaction. So H+ equals 10 to the minus pH. Okay, so worked example. Again, you should be able to do it now. I've given you the formula, so have a go. What is the concentration of H+ in a solution of pH 5.2? Okay, I'm sure you've managed to do this one as well. So my H+ concentration, 10 to the minus pH, so 10 to the minus 5.2, which gives me a value of 6.31 times 10 to the minus 6. So this is why we calculate pH, because there would be no way we would know that 6.31 times 10 to the minus 6 would be equal to the pH we're given in the question. So that's why we use the pH scale. Okay, if we carry on. So calculating the pH of a weak acid. Okay, so this is slightly more difficult, but again, it's not really that difficult. I think you should be able to get the hang of it quite quickly. Again, we're just going to write the definition. So a weak acid definition is an acid that partially dissociates and an example, the most common example that you will see is ethanoic acid. And I can write ethanoic acid up here. And from my definition, I know that it's going to partially dissociate to produce this. Okay, which this is, we write it down so we don't get confused. Ethanoic acid produces the ethanoate ion and obviously the H+. Okay, so we can work out a K expression. Okay, and my Ka expression is the concentration of my products here over the concentration of my reactants. So that means my Ka would be over my concentration of H+. And I forgot to mention that my Ka value is, we call the acid dissociation constant. And it gives us the feel of the strength of the acid, but I don't want to go into too much detail about that just yet. So all I'd like you to be able to do is be able to draw or write these Ka expressions. Okay, so this value gives us a feel for the strength of acid and how much it dissociates in water, as I just said. But the most important thing is to be able to calculate to derive these expressions. Okay, so to calculate the pH of a weak acid, some assumptions are made. So this expression we use to calculate a weak acid is Ka equals H+ squared over the concentration of the acid. E.g., if I was going to take my example of my ethanoic acid from here, my Ka expression would look like H plus squared, that hasn't changed, over concentration of my original acid. So this would be my original acid. Okay, makes sense so far? Hopefully does. So why do you think we can make these assumptions? Yeah, and I'm going to let you have a think about it and then we'll come back and go through. Okay, so we've made some assumptions, yeah, and we've basically said that up here that my H plus must be equal to my concentration of the ethanoate ion. So my H plus concentration is equal to my concentration of the anion, which gives me H plus squared. Okay, the reason for this is because we just make this assumption. Technically it's not true, so we'll just fill this out. So technically there will be slightly more H plus ions due to the dissociation of water. But we say this value is insignificant for most weak acids, and what I mean is that the acid is dissolved in water, and water will set up this equilibrium, so we will have some extra H plus, but this amount is so small that we can just think of it as irrelevant. And the second assumption we make is that my concentration of my acid, which is undissociated, is equal to concentration of the acid at equilibrium. We can just fill this out. So the concentration of the initial acid is the same of the acid at equilibrium. And really, technically, it's not. But again, so little of the acid dissociates that it does not affect the pH value for most weak acids. And that was what I was saying about the equilibrium in weak acids. So the equilibrium in weak acids, I've written that really the wrong way around, lies so far to the left that we can say that it's insignificant. Alright, so you're generally not asked about these in an exam, but it's good to know where these, or this expression of Ka comes from. Okay, so moving on. So a worked example. So now I've given you the steps to be able to work this out. So I think you might be able to do it yourself. Okay, so have a go at it, see how you get on, and then we'll go through it together. Okay, I reckon most of you have done this. So what is the pH of 0.1 mole DM-3 of ethanoic acid with a acid dissociation constant of 1.74 times 10 to the minus 5. First thing we need to do is write the Ka expression, and oh, that seems to be Kc, so that should be Ka expression. So my Ka expression for calculating this would be H plus squared over Ha, or you could have written ethanoic acid in here. I'm just going to leave it as that for a second. Rearrange to make H plus squared the subject. So H plus squared equals, bringing this up, Ka times by concentration of the original acid. Then I would take the square root of the acid using this formula. Okay, now I'm just going to put the values in here. So rearrange to make h plus squared the subject. So we would have calculation would be 1.74 times 10 to the minus 5 times by my original concentration 0.110, which gives me a value of, what does it give me a value of? We'll just leave it as h plus squared at the minute. And now I can do this calculation down here. So it equals 1.74 times 10 to the minus 5 times by 0.1. Take the square root, which gives me a value of 1.32 times 10 to the minus 3. Okay, I can then calculate my pH. Now I have my concentration of the acid using this formula times 10 to the minus 3, which gives me a value of, what do we have a value of? 2.57. Okay, so again, I think it's quite an easy calculation as long as you can rearrange the equation and you can remember the equations and the expressions to calculate a weak acid. Okay, again, this is another worked example that I think you might be able to do, so have a go at it and I'll go through it when you get back. Okay, so calculating the Ka of a weak acid. If we know the concentration of the solution of a weak acid and the pH, it is possible to calculate the Ka of the acid. So, worked example, 2-nitrophenol is a weak acid, 0.1 mole DM-3. 2-nitrophenol has a pH of 4.10. What is the Ka of 2-nitrophenol? Okay, well, the first thing I need to do is I'm going to have to work out the concentration of H+. I have a pH here, so my H+ concentration equals 10 to the minus pH, so 10 to the minus 4.10 gives me a value of 7.94 times 10 to the minus 5. Okay, now I can add this to my Ka expression. I've worked out the concentration of H+ up here. I know my concentration of HA down here, which is 0.10, so 7.94 times 10 to the minus 5 squared over 0.100. I can put this value in and it gives me a value of 6.38 times 10 to the minus 8. Okay, again, I think these calculations are okay so far, so we will carry on. Okay, so moving on to pKa. So although the Ka value can give us a feel for the strength of the acid, it's hard to tell by looking at these very large or very small numbers, as we just figured out there. So therefore, pKa, just like the pH scale, makes it easier to see the acidity of a solution. The pKa makes it easier to determine the strength of an acid. Again, there's another formula that you need to know. So we can calculate pKa as pKa equals minus log to the base of Ka. So you may recognize that it works in a very similar fashion to pH. So calculate the pKa, two acids with the Ka values of 1.6 times 10 to the minus 4 and 1.3 times 10 to the minus 5. You can do this yourself. Okay, so have a go. Okay, I'm sure you've been able to calculate this, so we'll just get into the habit of throwing this again. So pKa equals minus log to the Ka, which equals my Ka value minus log of 1.6 times 10 to the minus 4, giving me a value of 3.80. And over here, minus log of 1.3 times 10 to the minus 5, giving me a value of 4.89, which I'm sure you got as well. So the two methods, the two acids are methanoic acid and ethanoic acid. And therefore, the lower the pKa, the more acidic the acid. Okay, so the lower the pKa, the more acidic the acid, and we could say the stronger the acid. Really, it depends on how much more it dissociates to produce these H pluses. Okay, so right, so we'll stop there because we've done quite a lot of work on acids, on strong acids, on weak acids. So we'll have a pause and then we'll come back and do the ionic product of water. Okay, so the ionic product of water. Right, so it's useful to know where this comes from or is derived from, but you don't really need to be able to explain it, so we'll go through it quite quickly again. So pure water dissociates according to, as you know, H plus OH minus. Right, so write out the equilibrium constant for this reaction. If you've done equilibrium constants, you should have. We would have H plus, so my products over my reactants. I seem to manage to say that the wrong way around. So the products concentration over my reactants concentration. So pure water. So pure water is neutral. So if pure water is neutral, it must mean that the concentration of H plus is equal to my concentration of OH minus ions. If I had more H plus ions, then obviously it would be at a lower pH. And we can also say that the concentration of water is effectively constant, therefore we can simplify this expression to produce the ionic product of water. So I can get rid of this value and say that Kw equals concentration of H plus the concentration of OH minus. Okay, right, I want you to have a go at doing this question to get your head around it. So what are the concentrations at 298 K for the H plus and OH minus ions at this temp in pure water? Have a think about it and see if you can work it out. Okay, let's see how you got on. So from our writing up above, we said that H plus concentration equals to OH minus concentration. So we can say that, just to work this out, Kw is H plus squared. I know my Kw value, 10 to the minus 14, so my H plus must equal the square root. So my H plus concentration must equal 1.00 times 10 to the minus 7, and I know that my H plus concentration equals equals my OH minus concentration. Therefore, OH minus must equal 1.0 times 10 to, whoops, the minus to the 7, excuse me. Okay, right, so we can now say that if I look at this, so what is the pH? So my pH again is minus log to the concentration of H plus, which equals minus log 1 times 10 to the minus 7, which gives me a value, unsurprisingly, as 7. Okay, so this is where my neutrality of water comes from at 298 Kelvin, and this is where we can derive the ionic product of water. Again, you won't be asked to calculate that, however, it's good to know. So we will move on. So look at the equation above. There is an equation above, so I'm going to write one. H2O goes to H plus plus OH minus. This has positive enthalpy change. Okay. So look at the equation above. What will happen if we increase the temperature of water? Okay, so have a think about it and see what your answer is. Okay, so if we increase the temperature of this pure water, we should know that the equilibrium will favour the endothermic direction. Okay, so this is our knowledge from enthalpy. We know from this value sign that the forward reaction is endothermic, therefore the equilibrium will shift right. So I'm going to shift this way, which is going to increase my concentration of H plus and increase my concentration of OH minus. Therefore, increasing H plus concentration and OH minus concentration. Okay, so if I increase the concentration of H plus, what will happen to the pH? Well, the pH will decrease. Why will it decrease? Well, it decreases because pH is equal to my minus log of H plus. Okay, so it's measuring the concentration of my H plus. Okay, so let's read through this question and I'd like you to have a go at it. So at 30 degrees Celsius, the ionic product of water is 1.471 times 10 to the minus 14. Calculate the pH of pure water at this temperature. Right, have a quick go at this. Couple of hints. Remember that. Remember this up here. And see how you get on. Okay, let's go through the answer. Right, so well, we know that Kw, you can simplify it, say that H plus squared, because concentration of H plus is equal to OH minus. Which means that I can calculate my concentration of H, so 1.471 times 10 to the minus 14 square root, let's make that 14, equals my concentration of H plus, which gives me a value of 1.21 times 10 to the minus 7. So I've now worked out my concentration of H plus. I can then put it in to find my pH, which gives me a value of 6 point something, 6.91. I'll write over here so you can see it. So, what has happened? Well, that just proves our theory, which was further up the page, that as temperature increases, the pH will actually fall in pure water. So, that begs the question, so does water become acidic as temperature increases? Do we think that pure water becomes more acidic as temperature increases? Well, the answer must be no, because H plus is equal to OH minus. So all it means is that the pH scale is based on the neutrality of water at room temperature. If we change the temperature, technically we change the pH at which it is considered neutral. So we can just write below that pH of 7 is neutral based on water equaling H plus equals OH minus at room temperature. So it would still be neutral because the H plus would equal the OH minus. However, the pH may actually fall with increased temperature. Okay, right, so we are now going to move on to our last part. So calculating the pH of a strong base. So as like a strong acid, a strong base will completely dissociate to produce positive ion and hydroxide ions, e.g. we'll use the same example as we used earlier. So I have my Na plus, I have my OH minus. So if I have 0.1 moles here, it must mean, if it completely disassociates, that I have 0.1 moles here and 0.1 moles here. Okay, so we can use the ionic product of water to calculate the pH of the solution. Okay, so calculate the pH of the solution of sodium hydroxide with a concentration of 0.0500. How do we do this? Well, first thing we need to do is write down the Kw. Value. Okay, so H plus, Kw equals H plus and OH minus. Now when we're talking about the pH at room temperature, we will say that we can change these values to calculate the H plus. So I can rearrange this equation. So H plus is equal to Kw over concentration of OH minus. Therefore 1.00 times 10 to the minus 14 over my concentration of OH minus. I know it completely disassociates, so it will be same as the sodium hydroxide, which gives me a value of something. What does it give me? A value of 200 times 10 to the minus 13. Okay, I can then put my H plus concentration value into my pH, which gives me a value of 12.7. Okay, hope that makes sense. There is another way that you can go through it, and I'm going to quickly go through it. Yes, I will. Okay, so that's one way to calculate this, but I will also do another way in a moment. Okay, so you can use logarithms to calculate this. I think it's a lot more complicated in this way, but if you're good with them, it's fine. So we could say that, are you ready? We can say that log pH plus the log of OH must equal 14. Okay, yeah, it has to equal 14 because that is our H plus and that's our OH minus. Therefore, we can say that pH equals the minus log the concentration of OH minus. My POH log is equal to the minus log of OH minus, which means that pH minus log of OH minus is equal to 14. Again, stands to reason. Therefore, I can derive this to make pH equals 14 plus log of OH minus. So this is your important equation, and I can say then that if I take the log of OH minus, it would equal 14 plus, in my example, is 0.05. So the log of 0.05, and because we haven't got a minus, it will equal 14 plus minus 1.3, which gives me a value of 12.7. So, doesn't matter which way that you would like to do it. You can either do it this method up here, or we can use the logs down here. It's entirely up to you. It would always work out as the same answer. Okay, so I think most of them are quite easy and straightforward calculations, so we've gone through them quite quickly. If you're a bit unsure, then I would suggest having a watch through the video while you're reading through your notes. If you think you're okay with it, then I will see you next time. Hopefully it was useful, and bye bye.